is a joint work with Weiyuan Gong from Harvard, Zhenyu Liu from Tsinghua, and Zhenyu Cai from Oxford. And Weiyuan is also here, so if you can find him, you can ask him questions. So let's get started. Okay, so this work is about quantum learning. So what is quantum learning? So simply speaking, like quantum learning is about extracting information from target quantum systems. So I guess all the audience here agree that quantum learning is very important because it is a final step of all quantum information processing tasks. And it is also a bridge between the quantum and the classical worlds. Okay, and while quantum learning faces challenges, like sometimes if you want to extract certain information, you need to pay some price, and the price is sometimes fundamental. So, so in quantum learning, a very important task is to find resources for it that could benefit for it. So till now, two main resources considered for quantum learning are classical repetition and quantum memory. Like in many different quantum learning tasks, the trade-off between these two resources are established. So to show you how do these two resources work, I want to use the purity estimation to be a very simple example. Like in quantum information, the nonlinear properties are generally harder to estimate than the linear properties. So if you want to estimate the state purity, a very naive way is that you can first perform tomography to reconstruct the density matrix of your target system. And then using the reconstructed density matrix, you can classically compute the purity. Well, apparently this kind of naive method will require you to repeat the process many times. Well, actually, it has already been proved that if you only have the single copy operations on the target state, so like you don't have the ability to perform joint operations on multiple copies of states, then the accurate estimation of state purity requires an exponential sample complexity lower bound. This has already been theoretically been proved. Okay, well, if you have larger quantum devices, you can use swap test to estimate the state purity, like using this circuit. So if you can perform swap test, the sample complexity is only a constant. Well, you see that you need to, if the swap test algorithm requires you to double the system size because it requires you to perform some joint operations on two copies of the target state row. So you need to at least contain these two identical states. So you need to double your system size. So a very natural question we want to ask is that, can we avoid these difficulties? So basically, can we find some quantum resources that can help us to estimate properties without exponential sample complexity and without doubling the system size? So this is the problem we want to ask in this work. And in this work, we answer this question by considering the purification as a very special quantum learning resources. So what is purification? If you have a mixed state, you have a target mixed state, you know, because our universe is a closed system, so your mixed state is actually a subsystem of a larger pure state. So the larger pure state is called the purification of your target mixed state. And in this work, we mainly consider these four quantum properties, like the state purity. So here, rho A is our target mixed state, and we consider the state purity. We consider the virtual cooling properties. Here, the O is some observable. And we also consider the quantum principal component properties, like here, the rho A0 is the principal component of rho A. So basically, it is the eigenstate of rho A with the largest eigenvalue. And we also consider the quantum feature information. So here, in case you are not familiar with it, this is the definition of quantum feature information. Here, lambda are the eigenvalues of rho A, and phi AJ and phi AK are different eigenstates of rho A, and always some observable. So in this work, we mainly consider these four different nonlinear quantum properties, and we found that, and we already know that the quantum memory or the joint measurement between multiple copies of rho A is you can use joint measurements to accurately and efficiently estimate these four properties. And in this work, we consider the case that your target quantum state is a very large mixed state, but at the same time, the rank of your target mixed state is a constant. So this means that you can purify this state by only adding a very small number of ancillary qubits. So in this case, we found that if you can only perform measurements on this purification, you can also very efficiently and accurately estimate these 4 properties. So specifically, our work has 2 results, the upper bound results and the lower bound results. So for the upper bound result, we proved that given an n-qubit quantum state rho A and its purification with n plus 0.1 qubits. So by, I want to re-emphasize that by purification, I mean that the reduced density matrix for this global pure state phi AB is rho A. So we prove that these 4 properties that I mentioned before can be accurately estimated with a constant sample complexity and single copy operations on the purification. So you can see that according to our upper bound result, to accurately estimate these 4 properties, we avoid the exponential sample complexity, and at the same time, we don't need to double the system size. And at the same time, we also have the lower bound result. So basically, for fair comparison, we consider the case that the target mix state has a constant rank, and the rank is known. In this case, we prove that if for any protocol with only single copy operations on the rho A and without purification, requires an exponential sample complexity lower bound to estimate these 4 properties. And furthermore, we found that such exponential sample complexity also holds if you have some number of memory qubits. So you see that purification offers us an exponential separation in quantum learning tasks. Okay, so I want to sketch the proof of our results. So I understand that people hate listening to proofs, but I promise that this is really simple. So let me emphasize the problem. So you consider the case that you have a very large pure state phi AB. This is a very large pure state, and it has 2 subsystems. The first is A system, and the second is B system. And the system A is very large, and at the same time, the system B is small. So my question is that can you come up with some very clever way to measure the purity of rho A? And I want to give a hint to you. The hint is that it is really simple. So do you have some ideas? If you have, you can see it. Yes. Yeah. So yes. Right. So this is really simple. Why? Because we have this observation. So the purity of rho A equals the purity of rho B. So if you want to measure the purity of rho A, you can measure the purity of rho B. So because the rho B only has a constant number of qubits, so you can perform arbitrary, stupid protocol to estimate the purity of rho B. And the sample complexity, like you can perform tomography and then compute the purity of weight, and the sample complexity is a constant because the qubit number in system B is a constant. So it is not really possible that I get a QIP talk only by this observation. So let's move to the second task. Like in the same setting, you have a large pure state and 2 subsystems. How to measure this property? Like how to measure trace OA rho A square. Here, OA is some observable with a bounded norm. How to measure this? The hint is that it is not that simple. So I guess it is not very easy to guess the answer. So I will directly tell you the answer. So actually, it is based on very strange observation. This is the observation. So this is really strange. Like if you are a normal person and you want to get the square of rho A, you will multiply a very natural idea that you will multiply rho A with rho A, then you get the rho A square. So this observation tells you that if you have the purification of rho A, so this is the purification of rho A, you can multiply rho B on it. Here, I is the identity matrix. So you can multiply rho B on the purification and then trace out the B system. Then what you get is rho A square. It's rho A square. So this is, I think this is really weird, and this is a starting point for me to do this work. And although it is very strange, but it is very easy to prove. You can just use Schmidt decomposition to very easily prove this observation. So using this observation, we can rewrite our target property as in this form. So you see this this is very similar with like you measure the observable of OA tensor rho B on the purification. So according to this observation, according to this equation, we can design a very efficient protocol to measure this quantity. Like you can first perform tomography on rho B to reconstruct the density matrix of rho B, and then treat this whole thing, this OA tensor rho B, the matrix, as a new observable to measure it on the purification. And because the system B only has a constant number of qubits, and the norm of OA is bounded, so you see the protocol I mentioned is some complexity of my protocol is a constant. So according to these two examples, we can summarize that purification. The function of purification is that it can help us to filter out some spectral information of the target state. Okay, so I want to skip all the other proofs. Okay, so why our results are important? Like in some cases, if you can somehow get the purification of your target mix state, our results are important. Like for example, in quantum many-body physics, sometimes your task is to first prepare a very large many-body quantum state, and then estimate some local properties like the local correlation function or local entanglement structure. In this case, you naturally have the purification of your target local system. Then you can use our result to design some efficient protocols to do this. And in quantum simulation, if you are familiar with it, you see that some quantum simulation algorithms like the block encoding and the quantum purified query access model, they require the oracle to prepare the purification of your target mix state. So our results show that it is not very easy to replace this purification preparation oracle in these algorithms. And in quantum K distribution and random number generator tasks, sometimes you need to worry that the purification of your system is at a risk of being obtained by some third party to steal your information. Another very interesting corollary of our result is that if your system is suffering from a decoherent noise, then this means that the purification of your system is leaked to the environment. And our results imply that even if the purification, even if you only leak a single qubit information to the environment, this already cause an exponential challenge to quantum state learning. So this is a corollary of our work. So our results can also be utilized inversely. By inversely, I mean that instead of seeking for the purification of your target mix state, you can sometimes intentionally prepare a pure state and use our separation result to do something. A very typical example is in quantum cryptography. Let's consider a quantum verification task. Like for example, a client can control a quantum computer with only n+1 qubits, and the client want to perform a quantum circuit with 2n qubits, and the server claims that it can reliably control 2n qubits. And the question is that how can the client verify the power of the server? How can the client verify that the server can really control 2n qubits? So we found that we can use our results to design a protocol to achieve this. The protocol is like this. The client can first use its quantum computer to prepare a n+1 qubits quantum pure state. And then the client can treat the n qubit subsystem as the target mix state rho A. And then the client sends a constant number of copies of the state rho A to the server, only a constant copy, and then ask the server to estimate certain properties. The properties can be like arbitrary properties I mentioned before, like the one of the 4 properties I mentioned before. Then the client asks the server to report the measurement result back to the client. And due to our upper bound result, I forgot to say that the client should keep the single qubit state in its systems. And due to our upper bound result, you know that the client is very easy to verify the result because the client has the purification. So it is very easy for the client to verify if the reported value is right. Well, at the same time, the server does not have the purification. So according to our lower bound result, if the server can have the right answer, this means that the server can have quantum memory and can perform joint operations among multiple copies of the state rho A. And because the client only sends a constant number of rho A to the server, so you see this protocol can verify the power of server. Okay, till now, you may think that the advantage of purification is caused by the entanglement between systems A and B. Well, actually, we surprisingly found that it is not really, it is not necessarily quantum. So we prove that the advantages for estimating state purity and this virtual cooling property and the quantum principal component properties are not necessarily quantum. So the advantages for estimating these three properties can be achieved using this state. So you see this is a classically correlated state between systems A and B. Like here, the lambda J are eigenvalues of the reduced density matrix rho A and rho B, and the phi Aj and phi Bj are eigenstates of the reduced density matrix rho A and rho B. We found that if you have this classically correlated state, we can recover the advantage of purification in estimating these three properties. Well, at the same time, we prove that the advantage in estimating feature information is actually quantum. So we theoretically prove that with the classically correlated state, estimating quantum feature information is also, the sum complexity is also exponential. So we cannot use classical correlated state to replace the advantage in estimating quantum feature information. Well, another thing I want to emphasize is that although the advantage of purification can be sometimes replaced, the purification is more robust compared with classical correlation. Because like if you use classically correlated state to estimate these properties, we require this specific form quantum state. So you say that this is not robust under some like global unitary perturbation. Okay, so let's summarize. So the take-home message of this work is that in this work we prove that purification is a very useful resource for quantum learning, and an exponential separation in sum complexity exists. And if purification can be easily acquired, one can design efficient learning protocols using our results. And our results also find applications in quantum cryptography. And I also want to mention that because of the time limitation, there are some important points in our work I am not mentioned in this talk. For example, in our paper, we discuss how to extend our results from quantum state learning to quantum channel learning. And we also compare the power between the purification and more memory qubits. Like now, I only tell you the comparison that the purification has some advantage compared with a small number of memory qubits. But what about the number of memory qubits is large? You can find it in our paper. And we also use our purification results to design a protocol called the blend observable estimation. Okay, you can find this results in our paper. Okay, and I want to mention a very important future direction. So like in this work, we find a new resource for quantum learning, which is purification. So can we find other resources for quantum learning? Like for example, in this very nice work, they show that the conjugate state can also be a quantum, can also be a resource for quantum learning. So can we find something else? With this, I want to thank you for your attention.
Yeah, we can open up the floor for questions.
Thanks for the nice talk. I think actually for getting a purification of a mixed state, there could be multiple choice. I wonder, in your case, does different purification give you equal amount of advantage, or there could be some preference to choose some specific ones?
Yes. So like for example, you see the advantage for estimating state purity that you can directly perform estimating the purity of the purification. So you see that so actually we want you to have the smallest purification. Yeah. So this is we have some preference.
I see. Thank you.
Congrats on the nice result. I'm just wondering, so your purification, it's constant number of ancilla. So if you have polynomially many of ancilla? Or do you still expect such a exponential separation? Because in this case, your row A, your upper bound is guaranteed to be low rank.
Yes, yes. So yes, so our result can be generalized like here. In this work, we only focus on the case that row B have a constant number of qubits because we want to have a separation between constant and exponential. So if the so the advantage of purification can be generalized for a larger number of qubits. But it is like you said, you can have a polynomially number.
Yeah, if row A is full rank, do you still expect the separation?
Oh, yeah. Oh, I don't expect the advantage. Yeah. So at least the this system should be smaller than your target system.
Yeah. Can I expect that your separation come from the fact that row A is just the spectral information is?
I think the answer is no. Like because like in our lower bound analysis, we already assume that the rank of row A is constant and known. We found that even in this case, then the state learning is also exponentially hard.
Yeah, but your upper bound will be, the algorithm will be harder. You need more samples for upper bound, right? If row A is higher rank.
Yes.
Sorry, maybe we can move it offline.
Oh, yeah. Okay.
Question. So you are, I'm sorry, I didn't understand so clearly, but you are considering the estimation of trace of rho square.
Yes.
But that problem is somehow special case of the estimation of linear entropy.
Yes.
And this one is already studied several papers.
Yes, of course.
How
But
about the conversion? For example, that Wagner's group, they already discussed that problem, Wagner.
yes, but we consider that the purification is helpful in this task.
Helpful. So
Yeah. I mean, like if you don't have purification, then estimating this is exponentially hard. If you don't have quantum memory, if you don't have joint operations. But we found that if you have purification, then this is the sample complexity can be exponentially reduced.
Okay. And I have another question. So you consider blind estimation in the final part. What is this?
Yeah. So we design a protocol that so this blind observable estimation. Yeah. Okay. For details, you can see the paper. But generally speaking, it's a protocol that, for example, I have a quantum computer and I'm very good at preparing some states. But I have an analog quantum simulator. I'm very good at preparing some state, but I'm very bad at measuring observables. So I want to send my state to another quantum computer and ask the computer to help me to measure the observable, and then ask him to report the measurement result back to me. And by blind observable estimation, we mean that we can make sure that we can get the correct measurement result from the data reported from the other quantum computer. Well, at the same time, the other quantum computer cannot have the correct expectation value. So this is blind observable estimation, very similar with something like the blind quantum computation.
So also I have another question. Did you calculate the Fisher information of this problem? So this problem can be formulated as the one parameter estimation with nuisance parameter.
Oh, you mean in this blind observable estimation?
No. This trace of rho sigma. Yes, this quantity. So the estimation of this quantity can be formulated as Fisher information. You already calculated the Fisher information with how to say nuisance parameter. Did you formulate this way? Yeah. This is one parameter estimation with nuisance parameter.
You mean which task, like this task or the Fisher information task? Or you propose some other protocol to estimate this protocol?
Maybe you didn't know that formulation, that situation, there is a one parameter to be estimated, but you do not know the other parameters. So in that case, the problem is formulated as a parameter estimation with nuisance parameter. So in that case, you need to consider some projective Fisher information in some sense. and this one give some asymptotic performance. Of course, in that case, you need to fix the system size, and then you need to increase the number of copies. So in that case, you can achieve a bound is given as the inverse of the projected Fisher information. In the both setting, without a purification, with purification, you can calculate in the both cases.
So our analysis is not in the not based on quantum Fisher information. We use some like learning tree formalism to do this.
But in that case, this one gives some optimum bound. I know. But if he consider Fisher information, they should consider that kind of quantity. If you fix some system dimension and you increase n, so in that case, projected Fisher information is very important.
Okay.
And also, in some case, if you increase the dimension and n simultaneously, in that case, if you satisfy some condition, maybe Fisher information bound also achievable.
Okay.
I already discussed that problem in the case of the polynomial entropy.
Okay, I think
we can take this off this discussion.
Yeah.
Let's thank Zhenhuan again.
Thank you.